Swayam Prabha. Digital India. Educated India.
Hi friends, now we will have one tutorial session and this is based on the last 4 classes. We will see the problem number 1, which says the API gravity of natural gasoline and kerosene are 75 and 45 respectively. Determine the difference in their specific gravity and also explain the need of API gravity. Now, we will solve it. So, we have discussed in our previous class that API gravity is equal to 141.5 divided by specific gravity minus 131.5, and this is proposed by American Petroleum Institute. Now, in this case we have API 75 for natural gas and 45 for kerosene. So, from this relationship we can get specific gravity equal to 141.5 by API gravity plus 131.5. Why? Just we will take this way. So, this part if we take left side degree API plus 131.5. So, this is coming here. So, for one case for natural gasoline we have degree API 75. So, we will put it this 75. So, 141.5 divided by 75 plus 131.5. So, we are getting 0.685, but in case of kerosene we have the same formula. We will put degree API as 45 as given and then 131.5. So, it is becoming 0.802. Then what is the difference? This minus this. So, we will get 0.117. So, this is the difference in the specific gravity of these two oil. Now, the last part is what is the need of API gravity. So, we have specific gravity definition, then what is the use of this API gravity. Now, you see the difference in API gravity is 30, 75 minus 45 for the very small difference in the specific gravity. So, 0.117. So, if there is some other liquid fuel which is having in between, say this is 0.802, it is 0.685, so in between someone 0.07. So, this difference will also be less. So, smaller the scale, it will be difficult to identify the different components. So, once we can increase this in terms of degree API, that is 30 difference where 0.117. So, we will be having better chance to isolate and to identify different fuel properties which are important for certain operations. So, that is the use of API gravity unit. Now, in the next problem the statement says same amount of aniline and a lube sample is heated under specified conditions and these are mixed at 80 degree centigrade. So, to same amount it is mixed in the laboratory in a particular arrangement, then it is giving us 80 degree centigrade. If the specific gravity of the lube oil is 0.88, so determine the diesel index of the oil. So, we have the diesel index of that lube oil which is having specific gravity 0.88, and then it is also given that same amount of this oil and aniline mixes at 80 degree centigrade. So, we have already discussed that diesel index is equal to aniline point in Fahrenheit degree into degree API divided by 100. So, this is the formula. So, here aniline point of the present oil is equal to what? The temperature at which equal amount of aniline and oil mixes. So, this 80 degree centigrade, so it is converted to Fahrenheit. So, this plus this 176 Fahrenheit. So, we will be putting this one in as aniline point and degree API we have to calculate. The specific gravity is given, we have to calculate the API first. So, what is the API gravity? This is the formula we already have. So, now we will put it. So, 141.5 by 0.88 minus 131.5. So, 29.3 we are getting here. So, we will put this one in this expression. So, it is coming 176 aniline point into 29.3 API and divided by 100. So, it is coming 51.6. Our next problem says to break the water in oil emulsion, the crude oil electric emulsion in crude oil, electric field is applied during desalting operation to remove the salts. How would the force of attraction between the water droplets varies if the electric field is increased to thrice the previous value? So, this deals with a desalting problem. So, we have to predict that what will be the force of attraction will change, that we have to calculate. Force of attraction between the water particles or emulsified water droplets, we can say water droplets will experience that. Okay. So, we have already discussed in our previous classes that this force of attraction can be represented by this formula. So, where F is the electrostatic force between two adjacent droplets and E is the voltage gradient and K is the dielectric constant and D is the diameter of water droplets. This is D is the diameter of water droplets. S is the center to center distance between two adjacent droplets. So, this is known to us, we have already discussed. Now, the problem statement says that if the electric field is increased to thrice the power. So, electric field, what is this? Voltage gradient. So, voltage gradient is tripled. So, 3 times increase. So, if it is 3 times increase, the F will be 9 times increase, because this is proportional to E square. So, that is why the attractive force will become 9 times than the existing one. Okay. So, next problem 4, this says that during desalting process, after coalescence, the water droplets containing salt settle down in a desalter. How would the settling rate of these droplets change if the viscosity is reduced to half by increasing the temperature? So, when the desalting operation is taking place, if we increase the temperature, viscosity will be reduced, and it is given in this case that it is reduced by half, 50% is reduced. So, then in this case how the settling velocity will change. So, we can assume this as a laminar flow and then Stokes law will be applicable, and this is the formula of Stokes law. So, this V the terminal settling velocity, which is 2 into r square del rho, the density difference, and then viscosity of the media. So, now what is happening? This is inversely proportional to viscosity. So, what will happen in this case? The viscosity is reduced to half. So, viscosity is reduced. So, if it is reduced, then this will increase. Thus, if the temperature is increased to decrease the viscosity of half its previous value, the settle velocity will be doubled. Next problem says that the API gravity of West Texas intermediate crude oil is 39.6. What will be the volume of 1 metric ton of this crude oil in barrel unit? So, we know that 1 barrel is equal to 159 liter. Then specific gravity, we have this formula 141.5 divided by specific gravity, API gravity plus 131.5, already we have discussed in the previous problem. So, we will put this formula here. So, we are getting 0.83. So, this is the specific gravity of this. So, specific gravity once we get, that means that volume of 1 kg oil is equal to 1 divided by this 0.83, that is equal to 1.2 liter, that you know. So, then we have 1 metric ton. So, 1 metric ton means it is equal to 1000 kg. So, 1000 into 1.2 liter. So, that will be this much of liter. So, 1200 liter. So, if it is 1200 liter, then what will be that, what will be the value in barrel? We have to divide it by 159. So, we are getting 7.55 barrel. Next problem says Watson characterization factor and the US Bureau of Mines correlation index CI are used to determine the aromaticity and paraphenicity of an oil. Calculate the Watson characterization factor and correlation index of N-pentane, that is Tb is 97 degree Fahrenheit, Tb is equal to true boiling point and specific gravity equal to 0.63, and assess the nature of it. So, what type of compound it is, that is N-pentane. On the basis of the values which we will calculate, that is Kw and Ci, we can predict it. Okay. So, to solve this problem, we have to determine the Kw value, we have to determine the Ci value, and we have to compare these values with the standard one or with the literature value, then we will predict what type of compound it is. Now, we will see what Kw and Ci is. So, Kw is the characterization factor that is defined by or developed by UOP, and this is Ci, that is correlation index, is developed by US Bureau of Mines. The objective was to measure the what is the aromaticity and paraphenicity of any oil, and Kw is determined by this formula, that is equal to Tb to the power 1/3 and specific gravity by specific gravity at 60 degree Fahrenheit, and Ci is defined by US Bureau of Mines, that is 87,552 divided by Tb plus 473.7 into specific gravity minus 456.8. So, these are two formula, and it is also provided in literature that if Kw value is around 15, then it is highly paraffinic compounds, and if it is less than 10, highly aromatic compound, and for highly naphthenic crude it is 10.5 to 12.9 for a paraffinic crude base, if it is a, and Ci index, that is a correlation index Ci, that Ci scale is based upon straight chain paraffins having Ci value of 0. If it is a straight chain paraffin, then Ci value will be 0, and if it is a benzene, then it will be having Ci value of 100. So, these are the literature available. So, our objective will be to determine the Kw and Ci value first and to compare these values with this literature value. So, for the case, what is Kw? Kw is this. So, what is Tb? True boiling point, it is given 97 degree Fahrenheit. So, this Tb not in degree centigrade or Fahrenheit, it is in Rankine. So, that is we have to add 97 plus 460. So, this Rankine to the power 1/3 divided by 0.63, that is specific gravity it is given. So, we are getting 13.06. So, Kw is 13.06, already just we have discussed that around 13 or 15 it is paraffinic compounds and 10.5 to 12.9 for a paraffinic crude base. So, it is a paraffin one in heptane, and if we consider the Ci value, then this is the expression. So, Ci value is 87552 divided by Tb, that means 97 plus 460 plus 473 into 0.63 and minus this one. So, it is becoming 0. So, once it is becoming 0, that means it indicates that it is straight chain paraffin. And now, we compare N-pentane, it is a normal. So, straight chain and pentane is a paraffin. So, now it is solved, and by the value of the Ci and Kw we can predict what type of compound it is. Next problem says that a catalytic reforming plant produces hydrogen and benzene from cyclohexane by dehydroaromatization. In order to increase the production of hydrogen, the owner plans to change the process to steam reforming of the same feedstock that produces hydrogen and carbon dioxide. Stoichiometrically, what is the maximum ratio of pure hydrogen produced in the proposed process to that in the existing process? So, what we have to do in this problem? We have to see what will be the ratio of hydrogen production of the proposed process and the existing process. Existing process is dehydro aromatization and proposed is your steam reforming. So, this process cyclohexane we have, this is the existing process dehydro aromatization, and this is the second process which the owner is proposing to reform it in presence of steam in this form. So, 1 mole of cyclohexane if we consider, then it is giving 3 mole of hydrogen, the existing process, whereas the proposed method is giving 18 mole of hydrogen. So, what will be the ratio? 18 divided by 3, that is equal to 6. Next problem says a gasoline mixture is formed by mixing different types of compounds as provided in the following table. Determine the requirement of N butane to make this gasoline with rate vapor pressure RVP of 10. The RVP and molecular weight of N butane are 52 and 58 respectively. So, this table shows us some data, that is our base stock, that this is a blend, gasoline blend, which is having LSR gasoline and then reformate and then alkylate and FCC gasoline. So, straight run gasoline and then reformate, alkylate and FCC. So, we are mixing with this, is barrel per day. So, it is 4000, this is 6000, 3000, 8000. So, these are the production, we will mix it and then we will get some mixed gasoline. So, in this BPD it is, this is pound per hour, these are the pound per hour, mole per hour is this one, you converted, and mole percent this, it is given. So, read vapor pressure for each component is given here also. Okay. Now, we have to decide what amount of N butane, we can add with this mixture, so that overall RVP we can get 10. So, this is the problem statement, and we have to determine what ratio, what will be the ratio or what will be the mole per hour here, what will be the mole per hour of this N butane. So, that will give us the 10 RVP. So, that is the statement. So, now in this case we can assume that the after mixing, what is the mass of this we are getting, the total moles of this, how much total moles of the blend we are getting, and what is the RVP of the total blend. So, that is equal to individual component which we are getting, their moles and their RVP. If we sum it up, the moles and RVP of those the components, that will be equal to the total mass, total moles of the blended product into RVP of the blended product. So, this is the formula we will be using. We have in this case 4 components and we will be adding these 5. Now, we will be having 5 components. So, that way we can get. So, this is the formula, that is MT is your total moles blended of blended products, RVT is the specification RVP for products PSI, and MI moles of component I, and RVPI is the RVP of component I. So, in this case the RVP of the gasoline, original gasoline mixture will be how much? Original gasoline mixture we have without adding this N butane, this is your original we are considering. So, what will be the RVP? So, we can get mole per hour if we take 1 hour basis, so this will be a mole and this will be the RVP. So, this into this plus this into this plus this into this plus this into this, sum it up, then divide it by the sum of this. So, by adding these we are getting 2179, and then what we are getting here divided by 2179, this is not 2179. So, we will be getting 5.38. So, 5.38 we are getting. So, that is the RVP of the original gasoline mixture. Now, let the N butanol requirement is m mole per hour. So, what will be this m into the RVP of m, that is N butanol, that is 52, it is given in the problem statement, plus this the other one. Now 2, one is the original mixture, now butane 2 we are mixing. So, that will be this into this, and after mixing what will be the total moles of this plus m. So, that is 2179 plus m, and what is the requirement of RVP of this product? 10 as per the statement. So, this is equal to 10. So, this expression we are getting. So, from these expressions by summarizing we are getting this plus this equal to this plus this, rearranging this m we are getting 42 m is equal to 10,067. So, m is this divided by 42. So, 240 moles of normal butane is required. So, now we are getting 240 moles of normal butane is required. So, then we can make this table. So, what will be the normal butane? Our is 240 mole per hour. What is the molecular weight? 58. So, pound per hour 139.20 and then BPD is 1640. So, barrel per day. So, this is the requirement of N butane to make the blend which will be having RVP of 10. So, now we have solved the problem. Next problem says that how much heat required to raise the temperature of 1000 pound of a 40 API mixed base oil from 100 to 600 degree Fahrenheit. So, you have to determine here how much heat is required to raise the temperature of 1000 barrel of a 40 API mixed base oil from 100 to 600 degree Fahrenheit. So, how we can solve it? We have to define the average specific heat. So, average specific heat we have to determine within this temperature. If we can do it, then we will use it. So, mCp dt, that formula we will be using, mass into Cp into temperature difference. So, temperature difference in this case 100 to 600 degree. So, 600 minus 100 we will get, and then Cp we have to calculate, and mass is given 1000 lb. So, how can we get the average Cp? That is the most important part, and that can be determined in a graphical method. Some graphs are available as shown here. The specific heat BTU per degree Fahrenheit per pound, and here temperature with respect to Fahrenheit. So, if we see in this case we have two temperature, 100 and another is 600 Fahrenheit, and our oil is 40 API. In this graph we see different API are shown. So, 10, 20, 30, 40, 50, 60, 70 like this. So, our case is 40. So, we will consider this case, this 40 case, and we have temperature one is 100. So, this is our 100 and we have another 600. So, if we go up and we take this one, this line, so it is coming here. So, this value is almost coming below 0.5. So, it is around 0.48. So, specific heat at 100 degree Fahrenheit it is coming 0.48 BTU per degree Fahrenheit per pound, and specific heat at 600 degree centigrade it is coming here. This is below 0.8 and above 0.7, 0.75. So, it is coming 0.775, it is coming 0.775. So, from this graph we are getting this 0.775. Then what will be the average? So, we will be getting the average by this plus this divided by 2, this plus this divided by 2, that is equal to 0.627. So, the average Cp value is 0.627. Other way we can also get that 100 and 600, so in between is 350. So, if we take 350 curve and 40 degree specific gravity, then also it is coming the same value, that is your 0.627. So, now we are able to get the average specific heat. So, then we will apply this formula mCp dt. So, m dt and Cp, so we are getting this 3,13,000 and 500 BTU. So, now the problem is solved. So, in this session we have solved 9 numerical problems on this topic. So, thank you very much for your patience.